Demitri is going to tell us, doing a focus demo about the Trillian framework.
Well, thank you for inviting me and for everyone who's attending. What I'd like to talk about is a framework that I've been working on for several years now. It's called Trillian. So first of all, I'm with the University of Texas at San Antonio. So what is Trillian? So we're all very familiar with kind of a standard way of working with astronomical data, or more generally, scientists working with data. So you go to some data source, an archive, something like that. You typically manually download some data files. You have your own analysis code, and then you run your code against the data and get your results. And so this is a very common way of doing things. So this doesn't, so for the point of Trillian is to be able to do this on the cloud. And there are a lot of discussions today and for the past several years about how we're going to run data and analyses on the cloud. So my design, my vision for this is that I don't want to modify the user code at all. I don't want to work in a Jupyter notebook. I'm not saying we shouldn't do those things, but I want to take the exact same code that I work on my computer that reads data files, or that reads data, and then say, here are 1 million points on the sky, for example, that I want to analyze with my exact same data. So the idea of Trillian is that you take the user code, you pass it into the framework, it does everything of packaging it up, you provided a list of points that you want to operate on, and then it handles everything else after that. It figures out what cloud resources it has available to it. It throws things into a Docker container, and then it creates as many instances as are needed or as resources are available. And then the results will be returned to the framework, which then the user can use. And so I think there's a lot of power in this, in being able to just allow the user to run the exact same code that they do on the cloud as their desktop. So this, to accomplish this, there are some things that we need to consider. And one of those is, how do you access data? So if you use VO, if you use something like AstroQuery, code like that you can use to query data, but then when it queries the data, it goes to the archive that the data is located. It might go to IPAC or MAST or wherever. But the problem is that if I have data on the cloud, I don't want it to be downloading all of those individual pieces of information from all of those archives, because most of your time are going to be spent waiting for that data, and you're wasting those resources. So really what we want is for the data to be resolved by the framework rather than the user downloading individual FITS files. So as I've been developing Trillian, I've identified several pieces that could be independently useful, and I've been trying to create different Python packages so that they can be used separately from the Trillian framework. So I'm going to talk about some of those today. So these are the kind of a top level view of what modules I've created. Starting at the bottom, I'm going to touch on this. You'll see me use some of that code. If you're familiar, of course, a lot of people here are going to be familiar with Starlink, and specifically the AST library. This is a Python wrapper around that. Now there is one already, but it really exposes the C functions rather than a pure object, or like an object-oriented package, which is what Cornish is, and it sits on top of that. And so the functionality that I'm using right now is its handling of regions on a sphere. QLSC is well, let's go to the next slide, which actually describes this a little bit more. So I'll be talking about the Trillian Python module in more detail today. On top of that, there's a REST API. So I have a database that I've indexed WISE and SDSS and Galex and 2MAS and number of different data sets representing about 50 million FITS files. And so I have it's a database of metadata where all of that information is indexed, and that's used by the data resolver. I'm going to talk about science data descriptors, so I'll skip talking about that until I do. The QLSC, if you're familiar with the Q3C library, which is a PostgreSQL plugin, which allows you to index on a sphere. This is a pure Python version of that, so you don't have to use the Postgres library, and you can do everything that it does mostly. So it uses some of the code from Q3C, but then it adds more to that. And that's used for if you have a data cache and you have a million files, you're not going to stick them in one directory, and you're not going to, you're not going to stick them in one directory based on which instrument they came from, for example. So this allows me to create, basically pixelate the sky so that I can cache data. Anyway, I won't talk more about that. And then PG-AST is, again, I'm a big fan of the AST library. So that's embedded as a PostgreSQL plugin extension, so that I can use that functionality directly in my database queries. So the status of this is that this is, I think, what I'd consider a public preview. This is under very active development. Documentation is still coming, but I wanted to show people what is currently functioning and maybe get people excited about what it can do. So I want to emphasize that my focus on basically all that I work on, I really want to focus on the user interface. I want things to be as easy as possible for people to use. And so I hope you can see that's reflected in what I'm doing here. So I've kind of come up with design principles that just, as I've been working on this project, and that allow me to kind of focus on where I want to go with this. So one of the important things for me is that any information that can be unambiguously described should be able to be retrieved with nothing more than that description. And I'll give an example of that. Anything that's an implementation detail should be hidden from the user. And it turns out that most things are actually implementation details. I want to defer data retrieval until it's actually used. So if I have a description of data, then that description alone should be fine. And I don't need to actually retrieve the data until the user says, I want to actually display this data. I also think that metadata and documentation should be found alongside the data. Astronomical data is huge and varied, but to really use it, you have to go to a different website for each data set, and you may have to go to journal papers. Like if you want to find the PSF, best PSF for a particular data set, where do you go to get that? There's obviously no central location, and you may have to go to different, as I say, websites or journal papers, or somebody wrote something somewhere on a web page. Like all of this information that we use regularly should be found alongside the data. So I'll talk about that too. One of the consequences of these design principles is that you'll need an active internet connection almost all the time. That's because all of this information that I'm talking about, the metadata and whatnot, is enormous. But that's what search engines are for. I mean, we're not expecting to search the web without having an internet connection. So that's okay. It's just, this is one of the consequences. The other is that because we're talking about a lot of data, and I might perform a query and say, oh, I'm interested in these 10,000 objects. I don't want 10,000 FITS files to be downloaded onto my machine until I'm actually reading that data. So there's a lot of caching. And if I run a script, if it has to download some files, I want to be able to run it again and run instantly because those files are located in local cache. So consider this statement. So all images from Galex satellite within 5 arc seconds from this position, or any random position, in the far UV and the near UV bands. So those are just a few words, but this description completely and unambiguously describes a specific set of data. And that's powerful in a sense. Like if I were to tell an astronomer this description, if they're familiar with the massed archive, they would know that they could go there, and they would know, if you're familiar with the web interface, but those are now implementation details. Like what I've described is an unambiguous description of data. And if you have an unambiguous description of something, well, computers are really good at that. They should be able to give you what you want if you can describe something completely. So the location of the data, the format, whether the file is compressed on the archive, which HDU the images are located, how to look up the file based on the location in the sky, and what bands I've specified. These are all implementation details that have been described by this statement that I have here. So let's take a look at what that would look like in code. Can you see my notebook?
Yes, I can. But it's a bit small.
Yeah, I'm making it bigger. Yeah. Okay. So I'm starting with that description above. So this is, so let's look at some of the code that I have here. So I'm using the Cornish library to describe a region. So the description is 2 arc seconds from this position, using astropy to define that location. So I've got a cone, and then I have from my Trillian, so So all of the data that I have in Trillian is curated, and that's required because it has knowledge of that data set. So I want to use the Galex data set, and so I just say from the Galex data set, give me the images in this region, which is really just restating this in code. So if I run that, so that's run actually. So this says that 329 Galex images were found from that count search. So what did I get back here? I've got a list of images. So I just grabbed the first one here, Galex image 1, and I have this thing called Galex GR6 image. So now this is a more specific thing. It's specific, obviously, to the GR6 data release of Galex. What this is a subclass of an object I call Trillian image. This is obviously part of the framework. So a Trillian image is an abstract representation of an astronomical image. When we talk about an astronomical image or an image to an astronomer, they have a number of different things that are associated with that. So you don't think of an astronomical image as a 2D array of float values. You think of an image from an instrument in a particular channel of a location on the sky. So this image object, this Galex image 1, if I want to look at that image, I'm going to use the intensity property. So let's see what we have here. So Galex image 1 intensity is an object that's fits HDU, and that's exactly what it sounds like. It's a single HDU from a fits file. So it's an object that does some more things, but it basically points to a fits file and a particular HDU within that file. So from that, because that's the description, I can just say HDU.image as, let's see, or sorry, I can access the intensity and then the HDU number. And because it does ultimately have to be a file, I can get the file path. And so you can see here, this file is located in a cache. Where it's located, we kind of don't care. So let's take a look at that image. What would we need to do that? So all I need to specify is the data array. So Galex image 1.intensity.data, and that's it. And so I've got the image displayed there. So if I want to take a look at the header, well, I know that the intensity is a fits HDU object. I grab the HDU and then I get the header, and I've got that here. I'm not printing out all the cards. That's not really necessary. So the idea here is that this Trillian image provides a common interface across different data sets. So this was a Galex image, but there was really nothing specific to Galex in the code that I've shown here. Information about that was located within the class. So Trillian treats, just as kind of nomenclature, it considers data as part of a data set. So WISE is a data set, SDSS is a data set, and a data set release. So in WISE, there are a couple of releases. There's the All Sky release and the All WISE release. Both are All WISE and both are All Sky. So that's something to, that's helpful. So in this particular case, I'm interested in the All Sky release, which is different from the other one, which is that these are the collection of the single epoch images. So I import the data set from Trillian, and from that, so that's just a singleton object. And then I just say dot releases. So this tells me that there is the All Sky data release and the All WISE data release. So this WISE dataset object is aware of the releases that are part of that dataset. Now, you may not know, if you're starting to use Trillian, you may not know that WISE dataset is the right thing to use or what the names of the different datasets are. Dataset release, I have what's called a short name. So if you want to just say, give me a Trillian dataset release from wise.allsky or sdss.dr13 or galex.nuv, or sorry, gr6, it's a channel, then it'll just return that, that object to you. So if I'm curious to see the URL homepage for that release, then that's built into the framework as well. Okay, so now we have a data set we're interested in. So now I have that Galex image that I pulled out from all of the ones that were returned. I want to see which WISE images overlap that Galex field. I might want to do some combining those data sets together. So I'm going to use the Cornish library to get the polygon. So again, if I want to get the HDU header of that image, then I just say intensity HDU header. And then I can just create a polygon directly from that fits header. So now I have the points that describe the region around that image. And then I just say, here's my data set release, which is the WISE all sky. And I ask for the images in this particular region, and that's it. And so this shows that there were 80 images that overlap that region. This is just the first 10, just to show you here. Right. So let's grab the first one and plot it. So to do that, I've got the first image, and then I say again, image.intensity.data, and then plot it. And so there's the WISE image. So as I mentioned, the Trillian image is not a 2D array of values. It's an abstract representation of an astronomy image. So to an astronomer, like one of the common things you'll find associated with an image is a weight map. So let's say I wanted to view the weight map. So that's great. This is an abstract representation of an image. Astronomical images have weight maps. So if I want to plot the weight map, I just say WISE image 1.weightmap.data, and there's the weight map plotted. So just to complete this, let's see what the Galex weight map looks like. And so again, Galex image 1.weightmap. So this is probably starting to look a little tedious. I'm just plotting a couple of images and I'm accessing the weight map and doing this. But where did all of this data come from? Notice how nowhere in this notebook have I mentioned or referenced a .fits file, or I said fits open or anything like that, or referred to file names or paths. So the question is, where did the data come from? So my first answer is, who cares? These are implementation details. I had an object representing an astronomical image in the sky. I wanted the weight map, and so I said .weightmap, and I had it. I don't really care where the information came from. It was a specific and unambiguous description of what I wanted, the weight map of this file. And so I shouldn't have to go back to a web interface. I shouldn't have to go back to the documentation to find out where this weight map came from. So in reality, because we do want to pull back the covers a little bit, the Trillian framework knows about Galex, and it knows about WISE, and it knows where to get this information. So if we try to find out where these images came from, it turns out that this is the path of the image for the Galex file. And we see FD-INT to the INT, which indicates this is the intensity file. So that's the image, and the same thing for the but then, okay, and same thing down here for the WISE. But then for the weight map, it's actually located in a completely different file. It wasn't a different HDU in the same file. So when I said .weightmap.data, the framework said, okay, I need to know where the weight map is. And then the framework knows, like, oh, I actually know that the weight map is not located in the intensity file. I have to go find out which file it is, go and retrieve that file, and then grab the weight map data and return it to the user. And all of that is what happened above. So I didn't have to care about any of these things. So this is a convenience when working with, in this particular example, with working with 2 data sets. What if you're working with 10 different data sets or 15 different data sets, and all of them have weight maps, all of your images, all of them have weight maps, all of them have HDU headers that you need to get information from, but they're all going to be in different places. Sometimes they're going to be in the same file in a different HDU. Sometimes they're going to be in a different file. That's a lot of tedious work, and it doesn't scale to using large data sets. So that's basically what I've mentioned. So the thing is too, I mean, a lot of people, particularly ADAS crowd kind of people, it's like, well, I don't want you to abstract everything from me. I need to use that file. Well, that's fine. So if you want to get the file path, obviously the file is downloaded, it's placed in a cache locally. If you want to get the file path parameter, you have the direct access to the file. You can open it and pass it to anything you want. So the idea is that this doesn't strictly hide things from you if you don't want them to be hidden. So it doesn't prevent you from accessing any data that you want, but it provides an interface on top of the data so that you don't have to. So let's see what else we can learn from the WISE image we've been given. So I have my WISE image, and I want to find out what dataset release that it came from. So I just say .dataset release. And so I can see that I'm just printing this out here. It came from the WISE all sky data release. So what channels are available in this particular data release? Well, I can just do a little for loop here and say for channel and WISE data release.channels. And I can see I've got the W1, W2, W3, W4 channels. So again, all of this information, like none of this information is located within the FITS files I've downloaded, right? That's not where this information is located. This is information that's specific to the instrument and to the data set. But it's built into the framework. So if I'm working with a data set that I may not be completely familiar with, then I can say, what are the channels available, and just ask the data directly. Now, if I have these channels, maybe I want to get some more information about them. Which is the one, what is the central wavelength? What is the PSF size? What is the pixel scale? What is the 0 point? All of these things that you would normally have to find, what website you would have to go to, or what journal paper you'd have to look up, are all built in directly into the Python classes. And so that can be looked up there. So this information is useful when you're starting to work with data sets you're not completely familiar with, and you want to use them to combine with data sets you are. So building on this a little bit more, the idea is that we want to take information related to the data set and the instrument and put it into the framework. So one piece of information, it's not in your normal FITS file, is the filter response curve of the different channels, let's say for Galex GR6. Again, this information, if I were to say, again, I've got an object that represents Galex GR6, and I want to say, what are the filter response curves? That is a specific and unambiguous description of data, which means I shouldn't have to go anywhere to find it. So let's take
9 minute check mark. 9 minute check mark.
Okay, thanks. This is the longest part of it. So here I'm basically doing what I did before. I've got my data set release. So I request the channels from it. And then I'm just gonna skip through this. So basically from the framework, I'm plotting the response curves. Now, the interesting thing about this piece of code here is that I started with a single Trillian image, and I got a plot of the response curves and even properly labeled. None of this code here is specific to Galex. This could have been done with any image that Trillian has records of. Yeah, and then you can also do things like interpolate particular wavelengths. So that's a kind of a whirlwind tour of that. So the other thing that, let's see. As I was building Trillian, I realized that I needed some way to describe this data. So it's one thing for me at the top of this page to say, here's the description of the data in English, but I want a way to describe that in something that's a little bit more friendly for computers. What I realized is that I needed to describe data in such a way that specifically does not specify where it's located. In astronomy, we have our data scattered across numerous archives in different formats. And as I say, the data on the cloud needs to be there when you're running large scale compute, because you're going to spend a lot of time downloading otherwise. So I came up with this scheme called Science Data Descriptors, or SciDD as I've shortened it. So just as an example, this is a descriptor for Gaia data. So it has a SciDD prefix. Astro is like a top level domain. Then it's followed by data. It could also be file or model or other things that still could be defined. And then you specify a data set and then a data set sub-collection or a data set release. This is probably the influence of my days on SDSS. And then you specify a unique identifier within that release. So this points to, let's see, we'll just go to the demo here. So I have that descriptor here. So I need something to convert that descriptor into the actual data. And so that's a data resolver. I need to resolve that. So I have an API that I've written that does this. And so it converts basically this ID into a query, and then this pulled out the data here. Now I don't want it to look like, well, anyway, I'll get into that. So this is just an API. I mean, this isn't even Python anymore. Anything can be built on top of this. Now there is a Python, changed the name in my mind and changed everything. So there is a package, a SciDD package, which I've linked earlier, that actually implements this. And so, right. But this scheme is pretty flexible in that that returned an entire record. I don't really use Jupyter notebooks very much. That returned the entire record, but I may want just a couple of fields. In an API, you want to be able to specify just what you want. So this scheme allows you to do that. The DM stands for data model, which says of the data model, these are the specific names in that data that I want to retrieve. And then when I do that, just through the API, I get specifically that data. Now, I don't want you to think that the scheme is basically URL. They're similar, obviously, but they're not specifically URLs. There would have to be some code that translates the scheme into whatever the URL. And that's the thing, that's kind of the point, is that this is an abstraction. This is a description of the data, and how you get the data may change over time dramatically. But if you still have that description, then that should not change regardless of where that data should be. So let's see, let's do this really quickly. This is almost done. So here I have, let's say I have a file name. Maybe I found it in a journal paper. I have just a file name on my disk or something like that. Starting with that file name, this library will generate the SciID for that. So this shows me that it's Galex GR6 data release, and then this here refers to the point to the fact that it's a file, and this is the file. Now, notice that I don't have anything like a .gz or .zip. It may be compressed on the archive, but that's an implementation detail, and it's not specific to the data, not specific to the description of the data. So now I have this object, which is a SciD object, and let's say I want to open it. I want to read it. I want to get the polygon from that. So I say s.filepath. Well, nowhere in this code am I referring to, like this could be run on anyone's computer without having that file on disk. The moment I say s.filepath, that is a specific request for the data, which means if it's not found in the cache, then this command right here will actually go and fetch it and download it. And so now it can be used. So you don't have to think in terms of I need to download a file and open it. You just access the data from this description, and it will go and do all of that for you because those are implementation details. So in this case, what I did is I created a polygon and then did an image search. And this shows me, so there's the boundaries of that polygon. And then here are a list of files that overlap that one. And this shows you that these I've pulled up data DR13 SDSS images that overlap that particular Galex file. Yeah, so I'll just finish up here.
Yeah, we have 2 minutes if you want to take any questions.
Yeah.
No, you can finish it, but we have very few minutes left.
Okay. Yeah, so I'll post this. I just did that. Right. Anyway, so the point of this is that this can be done in a cloud environment, and that the code that I have running on my laptop doesn't know where the data is, but it uses this abstract description of it. And you should be able to you can take that same exact code, place it on the cloud, and run it there. So yeah, I'll just leave it at that.
Thank you, thank you, thank you. There is a question from Sarah Weissman, who is wondering about GraphQL. Is your data description language something similar? Are you solving the same problem, or is there a difference?
I've looked at GraphQL a few times, and maybe someone can correct me if I'm wrong, but the impression that I've had is that it's very much tied to the database schema. And to me, I don't want to tie the data access to any particular schema. That requires users to potentially know what the schema is, or if the implementation of the data access or the data storage changes completely, then that breaks along with it. And so I'm really trying to make an abstraction there. Now, that doesn't mean that GraphQL can't be used as the implementation detail to retrieve this, but that's not a detail. That's not something that I want to expose to the user.
Okay, thank you.